Right. Our last speaker for today is Mike Graham from University of Wisconsin, and he's going to talk about Tollmien-Schlichting route to elastoinertial turbulence in channel flow. Please go ahead.
Okay, lovely. So thanks so much for coming to my talk. Thank you very much to the organizers. This is an amazing meeting. I'm so happy to be here seeing people in person. So I'm going to talk about mostly recent work on trying to gain a little bit more understanding of the phenomenon of turbulent drag reduction. So you've heard about that previously in this meeting. In particular, you heard from Yves about some of his work. So what I'll talk about is our recent work, and I want to point out that this is collaborative with Beverly McKeon's group at Caltech, and some of the well, I'll point out specifically some of the linear analyses that have informed us on this in this area. Okay, my group likes ice cream, so all of our group pictures are eating Wisconsin ice cream. Okay, so many people will have in the turbulence field will have seen this picture, or a picture like this. So this is firefighters testing water here, and water plus polyethylene oxide. And so in the 1960s, Union Carbide marketed this to firefighters as rapid water. So I'm presuming this was a constant pressure drop experiment. And what you see is that the polymer solution, the stream of the polymer solution goes much further than the water. Okay, and so that's very appealing from the point of view of a firefighter. More generally, turbulent drag reduction by polymers or surfactant solutions, which is another interesting story, is very appealing for people who need to pump fluids long distances. And so drag reducing polymers are very commonly used in the pipeline industry, for example, in lots of situations involving pumping fluids. So one fun little anecdote: why isn't this used in firefighting today? It's not. And so I contacted someone who sells equipment to firefighters and asked why that's the case, and he pointed me to a blog, nycfire.net. So in FDNY, rapid water was used only for a few years. If you bled the line in the hallway and the proportion was incorrect, the floor became very slippery. So anybody who's worked with polymer solutions or other complex fluids, Björn is nodding his head, knows that these are kind of stringy, gooey fluids. Even when they're very dilute, and I'll talk about that, they're quite stringy. Okay, so despite it's not being used in firefighting, it's used in other applications, and more fundamentally, we're very interested in just understanding how we get such dramatic drag reduction in this application, and are there any lessons for other types of flows. All right, so since this is primarily a turbulence crowd and not a polymers crowd, I have just one little slide of tutorial on dilute polymer solutions. So the fluids that, or the materials that are effective for turbulent drag reduction are long chain linear polymers. Okay, and so at equilibrium, they have a random coil configuration, and that gets unraveled in flow. The way we typically model that is with a very coarse-grained model that just captures the end-to-end distance between the two ends of the molecule, and then there are little beads that experience Stokes drag and Brownian fluctuations. And one thing and then there's a spring that accounts for the entropic restoring force of the polymers trying to get back to their equilibrium configuration. All right, from the point of view of a turbulence person, the way to think about a polymer molecule is it wants to stretch like a material line in flow. All right, but it relaxes because of this entropic force. Okay, so as soon as you think about evolution of material lines in complex flows, chaotic flows, you start to understand you can have things like exponential stretching of the material line, and you can have exponential stretching of a polymer molecule in an extensional flow. All right, and that's key. So shear flows, so material line stretching is linear in a shear flow. Polymers are hard to stretch in a shear flow, but any flow that has an extensional component, there'll be exponential stretching of material lines, and the polymer molecules will try to stretch exponentially as well. Okay, and so that becomes important. And so turbulent flows, from the Lagrangian point of view, are extensional. Material lines stretch exponentially fast. All right, and so polymer molecules will try to do that too. All right. One thing that a lot of people were working on for a while was, okay, we know about turbulent near wall structure. We know about exact coherent states, quasistreamwise vortices in the wall region. And how I got into this field many years ago was by seeing a talk by Fabien Willef on exact coherent states in channel flow. And we thought, well, maybe this is a way of understanding something about polymer drag reduction. And we were having conversations earlier in the week about coherent states and their value mechanistically for thinking about flows. And it turns out that there's value in the polymer case as well. So this actually is quite old work from my group. So this is a channel flow ECS. This is one of Wally's exact coherent states. And what we've done is basically find the first effects of viscoelasticity on that coherent state. All right, so this is channel flow. This is a half channel, the bottom wall here. So we have these staggered quasi-streamwise vortices, and the panels here are polymer stretching. All right, and here we're increasing the Weissenberg number, which was on my previous slide, which is the product of a characteristic strain rate, we use the wall shear rate, and a relaxation time. So Weissenberg number goes up, means the polymers are relaxing more slowly with respect to the flow. All right. So as Weissenberg number goes up, you start to see the polymer stretch going up. And here at this Weissenberg number, you start to see the polymers stretched and sort of wrapping themselves around the counter-rotating streamwise vortices. And what's happening here, if you calculate the force exerted by the polymer, the divergence of the polymer stress, that's working against the vortices. So the vortex is trying to roll fluid up from the wall like that. The polymer stretching is large here, small here. The net force is trying to unroll those vortices. And so this is a very nice, clean picture in an exact coherent state. Lots of other people, including Eve, have shown something very similar just through direct numerical simulations of turbulent flows. All right, so we actually understand pretty well how the polymers suppress the near wall structure. All right. And but then what happens as you keep going up is that near wall structure collapses completely. The upper branch and lower branch solutions merge together. You settle a bifurcation. There's no more near wall coherent structure, according to this little picture. All right, and so we made that comment in this paper in 2006. And so, you know, what's next? What comes after these near wall vortices are suppressed? Okay, and so every once in a while, it's good to throw some speculations into your papers. Sometimes the speculations turn out to be productive or right in some parameter regime. Okay, so there may be lots of other things going on, other types of coherent traveling waves, temporal intermittency, TS waves, some kind of intrinsically elastic structures, yada, yada, yada. Okay, so something else has to be going on. All right, and we gained enormous insight into what that something might be through the work of Björn's group and Eve and others in 2013, where they did a beautiful study of what's now called elastoinertial turbulence. So experiments and simulations indicating that there was transition to a chaotic flow that could happen below the Newtonian transition threshold. And one particular thing that's valuable is the simulation results, and Eve showed some of these, where you see this basically two-dimensional polymer sheets of polymer stretching here. Okay, so this is and they're most intense near the wall in this case. All right, and so these are structures that don't emerge from any of the now classical exact coherent states studies, and so these are an important new target to try to understand how polymers are affecting turbulent flow. Then there's another very nice result. This is again from Björn's group, where they did a simulation, did an experiment in pipe flow where they quasi-statically increased the polymer concentration. And they did it at a relatively low Reynolds number. And what you see is the friction factor goes down quasi-statically, collapses to the laminar value. And then as they increase concentration, it actually goes back up a bit. And so there's a laminarization and a reentrant transition. Okay, that happens at low Reynolds number. If you increase the Reynolds number, then you see it, you don't see that reentrant transition. So the punchline of that is that points at two types of turbulence in polymer solutions, one that's suppressed by viscoelasticity and one that's promoted. So this branch and this branch, okay? And that's what really got us intrigued here. So that's what we're gonna study. All right, so we're going to try to understand something about this reentrant transition and connect it to other things that we know and other ways that we know how to study these kinds of problems. All right. Okay, so I'm not going to say very much about the simulations. These are the FENE-P model, which is that elastic dumbbell picture I showed you, but the dumbbells can only stretch so far. Direct numerical simulations, most of what I'll show you is 2D. Actually, the Eve's key insight in the PNAS paper was the importance of not putting in too much stress diffusion. And he spoke about that in his presentation. So here we use a high resolution central difference scheme that others have developed for viscoelastic flows that doesn't have a stress diffusivity term. All right. And we are interested in particular in the quite dilute regime. So 0.97 is this quantity beta, which is the ratio between the solvent and total viscosities. So beta of 1, there would be no polymer. Okay, so 1 minus beta is proportional to polymer concentration. All right, so quite dilute, which is I think it's a very interesting regime, and it's important for industrial drag reduction because you don't want to make the fluid too viscous while you're trying to reduce the drag. Okay, so this is a study that we did. This is channel flow. This is a study that we did in a Reynolds number of 1500. These are 3D simulations. And so we sort of took a different path through parameter space, but ended up seeing the same kind of reentrant behavior that, that Björn's group saw. So this is just friction factor minus the laminar value normalized. So there's Newtonian turbulence right there. We increase the Weissenberg number. The Newtonian turbulence collapses. The streamwise vortices can no longer sustain. But at higher Weissenberg number, we now see a chaotic state reemerging. All right. And here's what the structure looks like. This is at Weissenberg number of 7. So that's here, quasi-streamwise vortices. This is the structure at Weissenberg number of 20. These are, of course, vortex core visualizations. You see very different structure. So streamwise aligned, spanwise aligned vortex structure here. All right, so we're able to see in a different path through parameter space the same reentrant transition that Björn saw. The quasi-streamwise vortex structures completely collapse, and something else emerges. All right. One thing that I want to emphasize here is that the laminar state remains linearly stable in these calculations. This regime here requires a finite perturbation, but an extremely small perturbation. All right, and that's, I think, consistent with what other people have observed in their simulations. All right. So what does that look like? So this is just a slice through the a snapshot of this flow. The contour lines are wall normal velocity. The colors are the fluctuating part of the XX component of the conformation tensor. So that's the stretching along the main flow direction. You could look at the trace as well. It looks very similar because almost all of the stretching is in the flow direction. All right. And what's really striking here is the localization of the stresses in this particular case. It really looks like there's some sort of critical layer phenomenon arising here. All right. And that's kind of where the thinking started moving toward. Well, we know about critical layers. We know about linear stability, Tollmien-Schlichting waves, things like that. And so this picture here kind of shifted our thinking. And in fact, I was visiting Caltech and had a meeting with Beverly for a different thing we were collaborating on. And she had a picture that looked just like this on her desk that she wanted to show me. I'll show you that picture in a second. And that's what kind of triggered the view of this from a linear point of view. I should say that this kind of critical layer or wall layer structure shows up in other simulations. This is again from Eve's group. This is a section near the wall, and you see this layer where all the fluctuations are. This is a pipe flow DNS from Björn's group. So this sharp localization in a region near the wall has been seen by other people as well. And in fact, very common in these simulations. All right. So where does this all come from? All right. Okay. All right. Okay. So now let's start looking at some comparisons. So the top picture here, this is the snapshot that I showed you earlier. And then what we did here was we just looked at a power spectrum, the spatial spectrum. We did it in a line through the middle because there are lots of higher wave numbers here. And actually in this box, which is of length 10, the fundamental wavelength is 5. Okay, so we filtered that out, averaged over a bunch of snapshots, and this is that picture here. So you see this structure now. And what you see this is basically that the lowest wave number is this structure here. All right. This is the TS mode at that Weissenberg at these conditions. This is work from Beverly's student Ryan. All right. One thing to point out here is that the TS mode in the traveling frame has this famous Kelvin cat's eye structure, which means it has extensional stagnation points in it, and that turns out to be important. I think the picture that Beverly had on her desk was not the TS mode, but the leading resolvent mode, which looks like this. Looks almost like the TS mode here. Okay, so this was evidence of a link between elastoinertial turbulence, at least in this parameter regime, and the Tollmien-Schlichting wave. And so that's the topic of the rest of the talk. Again, so actually this picture here, so this is the same picture from Björn's group I showed before. This is recent work from Menqi Zhang, where they did the resolvent analysis for viscoelastic pipe flow. And again, they see the largest amplification in this near wall critical layer. All right, turns out this mode isn't axisymmetric. This is an m equals 1. All right. All right, so then what we did, those initial simulations were quite low Reynolds number. So we increased the Reynolds number to 3000, where the Newtonian Tollmien-Schlichting wave exists as a self-sustained structure. Javier, there he is. Javier did a simulation 30 years ago, finding that the 2D Tollmien-Schlichting waves in the Newtonian case exist down to about Reynolds number of 2700. So we picked a value above that. All right. And so this is just mean wall shear rate as a function of Weissenberg number. So there would be the Newtonian, the stable Newtonian TS wave. They're fairly straightforward to find in a 2D simulation if you choose the wave number correctly. All right. And as you increase, so there's a lower branch solution that's down here. And as you increase Weissenberg number, that one actually goes away. All right. But if you come down from EIT, all right, then you actually see a drop. So this is a blow up of this. So this is EIT. See a drop and then a very weak structure, which I've shown turning around here. I don't show that here. And so let's look at this structure, this very weak structure here. All right. Actually, let's just go to the next slide. So there's the TS mode. This is that very weak structure. All right. So it's very similar to the TS mode. The relative amplitudes of the polymer conformation components and the velocity components are in qualitative agreement with or nearly quantitative agreement with the TS mode. So this is a viscoelastically sustained Tollmien-Schlichting wave. All right. It's very weak, but it's there and it's self-sustained. And so then what we did was to move up in Reynolds number. So we move up from 3,000 to 10,000. Now you're above the linear instability threshold, of course, for the Newtonian TS wave. All right, and that I'll actually show you in a moment that the now those branches that were not connected at 3,000 connected at 10,000. All right, so if we take Weissenberg number at 10, just go up from 3,000 to 10,000. One thing that's interesting here is that there's a very sharp increase in the polymer stretching above about Reynolds number 6,000. One thing to notice, this is a log scale. All right, and this is the stagnation point stretch rate. So we remember those are hyperbolic stagnation points. So the material lines stretch exponentially. The threshold for a persistent stretching is Weissenberg number of a half. So the relaxation time times the largest Lyapunov exponent, which is just the principal stretch rate in this case. So when that exceeds a half, you should see persistent stretching at the stagnation point. And indeed, that's where, excuse me, that's where when you exceed this threshold, now you're seeing strong polymer stretching. So here, this is the stretching at 6,000. This is the scale here. This is at 8,000. Now you see the scale has changed dramatically. So now these Tollmien-Schlichting waves, their cat's eye kinematics are generating very large stretching of the polymer molecules here. Now at 10,000, we can, so we actually started at Weissenberg number of 10, and then came back to Weissenberg number of 0, came back to the Newtonian case. And you can continue back to 0, you'll get the Newtonian TS wave. You can go back, we didn't see any hysteresis. And so there's actually a continuous, and as far as we can tell, non-hysteretic path between the Newtonian TS wave and then here actually, here's at Weissenberg number 13. So this would be full-blown elastoinertial turbulence. So in the channel flow case, this EIT is directly connected with the TS wave. All right. And now one difference you see between the EIT case and this simple TS wave case. So here there's basically one sheet, all right, of stretched polymer. And you go to many sheets when you go to EIT, all right? And again, Eve showed this as well. And that was his observation initially. And so we can look at how this happens. So this is Weissenberg number 4. And we're doing this in a traveling frame. So actually in this, the stagnation point, the relevant stagnation point is kind of at the downstream end of the domain, the way we've chosen this. And so this is the same, this is the sheet that emanates from here. And what you can see is that it's flapping and there are pieces breaking off of it. And it actually breaks off when this is now when the normal velocity is downward. Okay, so that's a Weissenberg number of 4. So you're shedding these sheets. The Weissenberg number of 11, that just happens much more vigorously. And so it's like dealing a deck of cards or something. So you have this sheet shedding process going on. All right, in this case. All right. All right, and I think that's where I'll wrap up. I think I'm out of time. So we're starting to understand a little bit better how the interaction between turbulence and polymer dynamics. Okay, I think we understand pretty well that the turbulence, that the polymers suppress the near wall vortex structure. But now we also are seeing that they also excite this Tollmien-Schlichting-like structure. I would like to say I understand this. I think one path toward mechanistically understanding this is going back to the linear analysis and trying to understand why that mode is so dramatically amplified in the presence of viscoelasticity. I should mention that as we saw again from Eve's talk, there are other modes that come into play. There are center mode instabilities that were originally found by Shankar and Subramanian, but there are quite a number of people who've been studying those linear instabilities and their nonlinear evolution, and so those are part of the picture as well. I think in the dilute situation that we've looked at, those are, well, I think mostly people have looked at beta of 0.9 and larger there. But certainly the Tollmien-Schlichting story, certainly not the only story, but it seems to be a pretty clear part of it, and in particular in gaining an understanding of what's going on in the near wall region in these flows. And I think I'll just wrap up with that. Happy to take any questions.
Questions, yes.
Possible to ask question?
Yes, in a second. We have one question here first.
Yes.
Hi, Mike. Thanks. Very interesting. I'm just wondering if you ever had a region of the parameter space where you found like a pure traveling wave that you could connect to the TS mode, and if not, why you always have even weak chaos? Why do you never find it?
So that's a great question. We have tried to do the continuation of the viscoelastic Tollmien-Schlichting waves. We have not been successful in doing that. I will point out that even the Newtonian TS wave, as the Reynolds number increases, becomes non-periodic. And again, Javier, among others, has studied that problem. Yeah, we would love to be able to do continuation on this, but we were not successful at getting beyond relatively low Weissenberg numbers in our case.
Did you try and converge it, like with your edge states, for example? Did you just ever shove that into a GM res?
That's what we did. I mean, it was a Newton-Krylov time stepper was what we did. Right, so we were using our DNS to do time integration and looking for traveling waves from that.
Right, but never converged.
Not at a Weissenberg number we cared about.
Right.
Yes. And then the student graduates.
Thank you. I think there's a question online from Pedrak. Please go ahead.
No, it's me.
Hi, Victor.
Okay, sorry, Victor. Yes.
Okay. It's question about Weissenberg for coil-stretch transition. How do you define a Weissenberg for coil-stretch transition? You get 1/2.
We define the relaxation time is based on the stress. That goes as the square of the stretch. I think, are you wondering why it's not 1?
No. I wonder because for definition, it should be a Lyapunov exponent multiply on longest polymer relaxation time.
Correct.
Do you know polymer longest polymer relaxation time, or you use something else? I don't understand this.
So for those
other Weissenberg, you defined in different way through average probably velocity.
For the TS waves, let me just go back to that here.
Yes.
So what we did here is, so these are very nearly traveling waves. And so we can find the velocity gradient at the stagnation points. We just find the eigenvalues of the velocity gradient tensor there and take the largest one, and that's the stretch rate.
But it's related to Lyapunov exponent.
It's, well, for that, I mean, it's precisely the Lyapunov exponent for a linear flow, which, you know, near the stagnation point, it's a linear flow.
Okay. But
Okay.
it's fluctuating, therefore it's not clear because it's fluctuating flow. It's not linear.
Right. No, I agree. It is fluctuating, but only quite a small amount. All right. So we got a good estimate from just looking at the velocity gradient in the region near the stagnation point.
Excellent. Next question is from Joe.
Hi, Mike. Interesting talk. Sort of a change of pace on the question here. As someone who's tried to do polymer experiments in the turbulence regime, they're a bit of a pain in the ass to do repeatable experiments. I guess my question is to what degree does the FENE-P model actually mimic, you know, real polymers, and do you see any possibility of actually replicating behaviors as sensitive as you're looking at here in an experiment, given that, you know, if you get one batch of polymer, you get a very different behavior from the next batch, et cetera. The production control is really difficult.
That's right. So I don't, so there are a couple of questions kind of rolled into one there. So one is, how good is the FENE-P model? And I don't have it in this talk, but a long time ago, we actually did simulations where we just followed a trajectory in a Walefa flow, which is chaotic, and we did Brownian dynamics simulations with and without hydrodynamic interactions, and well, they're all finitely extensible, with and without excluded volume, so good solvent versus theta solvent conditions. And we compared that with the evolution of a FENE dumbbell with the same contour length and the same Weissenberg number. So the one fitting parameter was the relaxation time, which we found from the decay of the polymer stretch. And once you match parameters, we got quantitative agreement between the polymer stretching from the dumbbell model and from the more elaborate bead spring chain models. So we think the dumbbell model is actually pretty good. And part of the reason it's good in this flow is because chaotic flows are extensional. And so the distribution function, probability distribution, is fairly narrow for the polymer stretching. And in that case, FENE-P works. The other issue is that real polymers, anything that you buy off the shelf, certainly anything you would buy for drag reduction, is not monodisperse at all. Very polydisperse, and all of the action is at the high molecular weight end of that. And so if you used you know, a weight averaged, molecular weight averaged relaxation time, you might do okay. But then, of course, the polymers break, and then if the polymers break in half, the relaxation time is cut by a factor of 4, et cetera. So every polymer drag reduction experiment is transient in that, unless you work with like Julia Cornfield's polymers that actually can break and reform. But that's another. That's a very interesting story that I think would be interesting to see. Yeah.
Okay, so I think we need to cut here, and we will have more time to discuss. 4:10. We're going to have the discussion session starting. And so let's thank all the speakers once again. And yeah.